In this module, we discuss the coexistence curves of the phase diagram. In our previous discussions on phase changes, we focused on standard states where substances have specific melting and boiling points under set pressure. However, phase behavior becomes more complicated when we account for variations in pressure. This complexity is evident when examining coexistence curves, which are central to this discussion. The graph displayed here shows the coexistence curve for the two phases labeled phase alpha and phase beta. Each point of the curve, such as point A, signifies the equilibrium between two coexisting phases. If we move from point A to another point of this curve, the system stays in phase equilibrium, although at different pressure and temperature. This transition causes changes in both temperature, dT, and pressure, dP. Now we will uncover the underlying relationship between these two variables. To resolve this, we turn to the concept of chemical potential, which is intrinsic to each phase and varies with changes in pressure and temperature. The chemical potential's infinitesimal change for each phase is given by the molar volume times dP minus the molar entropy times dT. When two phases are in equilibrium, their chemical potentials are equal. Thus, for any infinitesimal change in pressure and temperature that keeps the system in two-phase equilibrium, the changes in chemical potential for both phases must be the same. After equating these changes, we obtain an expression that links the differences in their molar volumes and molar entropies with respect to the changes in temperature and pressure. This relation, derived from the equalities of the chemical potentials and their dependencies on pressure and temperature changes, is known as the Clapeyron equation. It states that the derivative of pressure by temperature along the coexistence curve is equal to the difference in molar entropy between two phases over the difference in molar volume. The Clapeyron equation is shown again here. An equivalent formulation of dP by dt being equal to the difference of molar enthalpy between two phases divided by temperature times the difference in molar volume is also often used. The Clapeyron equation can be applied to any phase equilibrium of any pure substance. The primary role of the Clapeyron equation is to determine the slope of a coexistence curve. It gives an exact description of how the coexistence curve behaves at any specific point and serves as a basis for the construction of phase diagrams. On the other hand, the Clapeyron equation also explains the shape and direction of coexistence curves on a phase diagram. For example, it shows that the direction of the coexistence curve is determined by the signs of the difference in molar volume and molar entropy between the coexisting phases. By explaining the course of the coexisting curves, the Clapeyron equation emphasizes the predictive power of thermodynamics and bridges theoretical thermodynamics with the practical phase behavior. Let us employ the Clapeyron equation to the solid-liquid coexistence curve, which characterizes a phase transition known as melting or fusion. The key characteristics of this transition are the difference in molar enthalpy and molar volume between the liquid and solid phases, represented by the enthalpy of fusion, delta fuse H, and by delta fuse V. We label the standard melting point at the standard pressure as T fuse standard, under the assumption that both delta fuse H and delta fuse V remain relatively constant across the temperature range of interest. We derive a straightforward relation for the slope of the coexistence curve given by this equation. Then the equation of the solid-liquid coexistence curve is given by this expression. One essential observation here is that the change in molar volume accompanying melting is extremely small. We have already mentioned on a few occasions that the molar volumes of condensed phases are in general small quantities. The differences between these small positive quantities are even smaller quantities. Consequently, the solid-liquid coexistence curve is a very steep straight line in a phase diagram. This fact was already taken into account in this equation by utilizing the standard value of the melting point instead of the current value in order to simplify the equation. Furthermore, as the enthalpy of fusion is almost always positive, the sign of the slope, or the direction of the solid-liquid coexistence curve, is basically determined by the sign of the change in molar volume. The direction of the solid-liquid coexistence curve, or in other words, the pressure dependence of the melting point, is illustrated in this figure. It shows lines with different slopes that represent the temperature dependence of the chemical potential of the solid and liquid phases. They intersect at a point corresponding to the equilibrium between these two phases. Typically, the molar volume of the solid is lower than the molar volume of the liquid. In such a situation, when pressure increases, the line corresponding to the chemical potential of the liquid rises more than that of the solid due to its greater molar volume. Figure A explains that this divergence results in a slight shift of the point of their intersection corresponding to the melting point to higher values. Now, consider the exceptional case, such as of water, where the molar volume of the solid is higher than the molar volume of the liquid. When pressure increases, the chemical potential of the solid phase of water rises more than for its liquid phase. Consequently, the melting point decreases slightly as depicted in Figure B. Such behavior can be also predicted by applying the principle of Le Chatelier. When pressure increases, the system tries to minimize its volume. Accordingly, there is a natural tendency for the system to favor the phase with a smaller molar volume. The equilibrium between phases can be restored by either raising or lowering the temperature, depending on the relative values of the molar volumes of the phases. For instance, in the normal case, if we increase the pressure, the solid phase becomes relatively more stable. Consequently, we need a slightly higher temperature to re-establish the equilibrium between the solid and liquid phases. Now we move on to the liquid-gas coexistence curve, which essentially characterizes the process of vaporization. As in the case of solid-liquid coexistence, there is a relationship between pressure and temperature during the phase transition. However, this relationship differs due to inherent characteristics of gases. To analytically derive an equation describing the liquid-gas coexistence curve, we assume that the enthalpy of vaporization, the difference in molar enthalpy between the gaseous and liquid phases, remains relatively constant over a range of temperatures and pressures. Considering the molar volumes, the molar volume of a gas is much greater than that of the liquid phase. This allows us to approximate the difference in molar volume between the gaseous and liquid phases to be equal to the molar volume of gas. If we further assume ideal gas behavior, the change in molar volume during vaporization is approximately RT over P. From these assumptions, we derive the relationship between the change in pressure and temperature during vaporization as dP over dt equals P times delta Vap H over RT squared. Unlike for solid-liquid coexistence curve, the slope of the liquid-gas curve is always positive. The latter equation can be reformulated as follows. The derivative of the natural logarithm of pressure by temperature is approximately equal to the enthalpy of vaporization divided by RT squared. The previously obtained result is known as the Clausius-Clapeyron equation. This equation emerges from the adaptation of the general Clapeyron equation for the liquid-gas coexistence curve. It allows us to investigate the relationship between pressure and the temperature of vaporization more deeply. To integrate it and obtain the equation of the whole curve, we need a reference point given by a known boiling point T ref at a specific pressure P ref. Common reference points include the standard boiling point or the coordinates of a substance triple point. Using the Clausius-Clapeyron equation, we can establish a relationship between the reference and new pressures and temperatures. Integrating both sides of our equation, we arrive at an expression that connects the change in pressure, the change in temperature, and the enthalpy of vaporization. When we rearrange and simplify it, we can express the vapor pressure at any temperature T as a function of the reference pressure, the enthalpy of vaporization, and the inverse difference of temperatures. The result is the equation for the liquid-gas coexistence curve. A crucial aspect to remember is that while Clausius-Clapeyron equation provides a reasonable approximation under many conditions, it is based on certain assumptions. The molar volume of the gas is much larger compared to the liquid. The enthalpy of vaporization remains constant over the temperature range of interest. Though it is a valuable tool, its accuracy, like that of all models, can vary depending on the specific scenario. The solid-gas coexistence curve characterizes the process of sublimation, where a substance goes directly from a solid to a gas. The mathematical derivation of the solid-gas coexistence curve closely mirrors that of the liquid-gas curve. The only difference is that instead of using the enthalpy of vaporization, we incorporate the enthalpy of sublimation. It is the difference in molar enthalpy between the gaseous and solid phases. The resulting equation reveals how vapor pressure due to the sublimation varies with temperature. All other parameters are used similarly to those in the equation for the liquid-gas coexistence curve. Comparing the liquid-gas and solid-gas coexistence curves with the solid-liquid curve, we can conclude that the liquid's boiling point and solid's sublimation point are much more sensitive to the change of pressure than the melting point of a solid. This sensitivity arises from the inherent nature of gases, namely their significant molar volumes. In practice, the solid gas and liquid gas coexisting curves are primarily determined experimentally. Nevertheless, the Clausius-Clapeyron equation, which we have used to deduce equations for the liquid gas and solid gas coexistence curves, can be also employed to determine the enthalpy of vaporization and the enthalpy of sublimation from the experimental data showing how the vapor pressure of a liquid or a solid changes with temperature. Now, let us zoom into the intriguing region where solid, liquid, and gaseous phases coexist, the vicinity of the triple point. This figure sketches a typical phase diagram around the triple point. Here we witness the intersection of three coexistent curves: solid gas, and solid liquid. We have mentioned that the solid-liquid coexistence curve can be represented by a very steep line in a phase diagram rising from the triple point. However, this sketch does not show exactly how extremely steep these lines are. In fact, illustrations of phase diagrams are typically heavily distorted in order to make the slope of the solid-liquid coexistence line visible. As solid gas and liquid gas curves converge at the triple point, it prompts an intriguing question. Can we find out which one between them is steeper at the intersection? To address this, we must compare the enthalpies associated with the transitions. At the triple point, the enthalpy change for sublimation, where a substance transitions directly from solid to gas, is equivalent to the combined enthalpies of melting, fusion, and vaporization. Since enthalpy is a state function, the sum of the enthalpies for these two consecutive processes, solid to liquid and liquid to gas, must equal the enthalpy of the direct solid to gas transition. Consequently, the enthalpy of sublimation exceeds the enthalpy of vaporization. When considering volume changes during these transitions, the molar volume of solids or liquids is practically negligible in comparison to gases. Empirical observations supported by our theoretical understanding reveal that at temperatures near the triple point, the solid-gas coexistence curve is steeper than the liquid-gas curve because the enthalpy change for sublimation surpasses that of vaporization. To finalize this module, we will briefly introduce Trouton's rule. This empirical rule states that for many pure, non-associated liquids, the entropy of vaporization at the boiling point is roughly constant and is around 85 to 88 joule per mole per Kelvin. The entropy of vaporization is the ratio of the enthalpy of vaporization to the boiling temperature. It can be well estimated as 10.5 times the gas constant R. The boiling temperature originally referenced in Trouton's rule is the normal boiling point, which is the temperature at which a substance boils under a pressure of 1 atmosphere. However, the difference between the standard and normal boiling point can be neglected for the purposes of estimating the enthalpy of vaporization of a substance. Trouton's rule is an elegant simplification based on the observation that when any liquid evaporates, the change in volume is fairly consistent across all liquids. Furthermore, the gaseous state of a substance is very non-specific, resulting in a very similar state of the substance after the evaporation. As with many empirical rules, there are exceptions. Liquids with strong molecular interactions that undergo significant molecular association in their liquid phase deviate significantly from Trouton's rule. This includes many substances forming hydrogen bonds in the liquid state, such as water and alcohols. Hydrogen bonds in liquids introduce a certain order and render them less random than many other liquids. Therefore, the increase in entropy when they vaporize is much more pronounced than for a liquid without hydrogen bonds.